So today, my office hours, I have to end them at 11 because I have another meeting. So I'll have extended office hours later. So homework 7 has been released. You should be able to see it, work on it. Based on what we talk about today, everything should go into scope, full scope. The homework is the last homework before the midterm. So everything on it is very important for the exam. So today, my goal is to finish attention. So almost done, but tiny bit more to say. Briefly talk about positional encoding. And then start into self-supervision. Which is autoencoding. Okay, that's the goal for today. So let's recall attention. Which we've conceptualized as a kind of soft, approximate hash table memory, like memory. And the way it works is that we quote store. We'll talk more about exactly what this means in a minute. Key value pairs. They're vectors. K, oops. So there's lots of them. Ki, Vi. And then you query them. Query using some Q, which results in the following operations happening. We compute a preliminary matching score, right, of EI, which is the match between, we can think of it as inner product, right, between key I and the query, which we normalized by the square root of dimension, where everything we're talking about here, the keys and the queries, keys and queries are in RD. So this computes like an initial score. How similar is the key I to the query? So this is, remember, this is just an inner product, right? This is just Q transpose key I. We compute this initial matching. Could be positive, it could be negative. Then we compute weights using a softmax. A weight alpha I equals e to the EI divided by a sum, j equals whatever, ranging over everything we can range over. Okay? So by doing this, we'll be dominated by the largest. This is like softmax style. So this has a couple of properties. these are probabilities. They're like probabilities. Right, they sum to 1 and non-negative. And it'll be dominated by the biggest, right? Because exponentials, the biggest exponential wins, right? Sum is almost like a max. So if you think about the sum as being basically a max of exponentials, then this is basically putting all of the mass on the biggest thing. So it puts a 1 on there and 0 everywhere else. Having computed these weights, alpha I, then we return the sum over j, alpha j, and then the corresponding values. Okay, so this is what it does. So important thing, there's no learnable parameters here. This is like a kind of a, you can think of it as a queryable pooling. Okay, it's a queryable pooling operation where you can think of it having, it looks at all these key value pairs, you insert a query, and out pops something which is kind of like a pooling, right? It's like somewhere between a max pool and an average pool, right? Where it's based on alignment to the query. Yeah, question?
Does V have to belong in the same dimension as query?
Great question. The question was, do the V's have to belong to the same dimension as the key in the query? And the answer is no. Nothing here requires that. For the mechanism to operate, you need to be able to take inner product type similarity between the keys and the query, so they have to be in the same space in terms of size, but the values are just being summed up, averaged together. No need to have them be the same. Okay? So you look at this operation, and now you can better appreciate why it is, we went very fast through this at the end of the last lecture, why it is that we do this normalization by square root of d. So we said last time, look, we're doing this normalization so that we don't have a huge qualitative dependence on this dimension d. So the reason we do square root is if we did nothing at all, no normalization at all, then what would happen is just when the dimension gets big, this inner product will get big, right? Just because you're summing up a bunch of things, so it can get big. When that happens, it means the scale at which the EIs operate will be very large. If the scale of the EIs is very large, it means that this alpha I will be more strongly dominated by the largest one. Okay? And so that's why you have to do something. And if you did that, then what will happen is that this return would basically be the appropriate max. And think about it, this whole thing is differentiable. So you want to see how do gradients pass through it. And if this is dominated by one thing, the gradients don't really go to everything else very much, right? Because they're getting multiplied by this alpha, and that's a small, very tiny number, okay? So at random initialization, you don't necessarily want to have that very strong max effect happening. So we talked about that. That's why you have to normalize by something. Now, the flip side is, why don't we normalize by d? Well, if we normalize by d, we would have another effect happening, which is that if these two things started off kind of at random initialization, this is basically a big sum, right? This is a sum of d entries. As a sum of d entries, the central limit theorem tells you that if all those entries are kind of similar in behavior, this thing is going to behave like something which is going to be like a Gaussian type thing, where its standard deviation will be square root of the number of things that are being added together. Okay? Which means if you normalize by d, all these e's would be very close to 0. if D is substantial, and if all these E's are very close to 0, then this thing is behaving too much like just average pooling. And it's not really sending anything that different back in terms of gradients. When you think about how it routes gradients. So you're not going to be able to break that symmetry very easily. So this is kind of the sweet spot in between. Not over-normalized like D would be, not under-normalized like doing nothing. Okay? You have a homework to kind of make sure you understand why this is the right normalization vis-a-vis the variance. It's a very short problem, just to make sure you all get it. Okay, any question on the mechanism itself? Like what's happening here? Just formally. Okay, yeah. Great question. The question is, we store these key value pairs. So where are we getting these keys and values from, right? And where are we getting this query from? And the answer, like anything else in the context of deep neural nets, is if you have something you need and you don't know where to get it from, you say that that transformation should be learnable. Okay? So you can think of these keys in practical context, these keys, values, and queries are the outputs of some multi-layer perceptron. Okay? So something is generating them. Now, we can think about whether it needs a nonlinearity. There's all levels of detail, but it's something learnable. Now the question becomes, well, sure, that's the output of a function, but what's the input to that function? Right? And that has to do with the details of the architecture, like what you're doing architecturally. So maybe this is a good time to talk about, like how this works in the context of the translation example we were doing last time. So recall the encoder-decoder architecture for translation, motivated by translation. Okay, so here, what you have is something, the encoder side. So we started with the idea that there's some RNN-based thing inside of this, okay? So we feed it in a 0, in comes x1, x2, x3, dot, dot, dot. Some xn, some length of the sequence that you're translating. Then the output of this goes into the decoder. So here's the decoder. And let's think about it in training time first. We already talked about how we'd use it at runtime. So at training time, this has a start token, and then the first output, and the second output. We're running it in autoregressive style. Until finally, we want it to generate ym, an end token. Okay, so that's the setup. So now the question is, how do we use this attention mechanism? So our goal, remember, was to do for these problems what the UNet does for image-to-image problems, right? So what we're going to do is inside of this decoder, what's happening inside this decoder, right? What's happening inside this decoder is we have some RNN set up. Right, and so on. We have many, many layers of these. And looking inside this decoder, so the initial state is coming from over here. for these RNNs, right? How to start, kind of basic architecture. And we were taking the output of the hidden state from the RNN, and we were feeding it in as inputs to the next level. Right. You can think of this as what's going on. Now, what we would like to do is we would like to add the use of this memory. So to use this memory, what we'll do is we want to give this RNN another input. You can always give something more input. Just concatenate the inputs together, right, from your learnable weight. It's like no problems. Take a new input in, right? So we want to give it something which is the output of attention. So I'll just draw it on the side here. You should think of it as part of this layer. So here's attention. So this thing needs to have a query, right? So you can ask for something. So how do you get the query? Well, you can take the state of this RNN, for example, and put a multi-layer perceptron, and this becomes the query. Okay? Now, in this setup that we have, what is it that we want to get access to? Like, where are these key value pairs being stuck in? Remember, this is like this queryable pooling operation is doing the routing that you in UNet you can do statically, right? It's telling you where to look. Okay? So the key value pairs that are coming in here, so let me like zoom. So here we have a bunch of key value pairs coming in. Where are they coming from? Well, they're coming from over here. Okay? So on this side, we have something that's populating these key value pairs, right? And that's on this side, in the encoder side. So the encoder has some multi-layer perceptron, which takes some input and populate these key value pairs. Now, in the particular case of translation, you can ask the question of where should these, what should be the input on this side? Does everyone see that as a question on the encoder side? There's many, many places you could put it. So at the encoder, again, you also have a basic structure. We started off with a default some kind of RNN. Typically, it's going to be LSTMs in these old style architectures. And you can choose to make these key value pairs in many different ways. So you can choose to have as the input to the MLP the entire hidden state of this entire encoder, which would be the combination of all of these hidden states going up. Right? Because that's all the state at the encoder, you might want to query all of it in principle. And that can be going into the MLP, which generates the key. Same kind of things can be going into the MLP, generating the values. You could also choose to do it kind of layer by layer. To say maybe what's happening, again, think about the UNet, right? If you think about somehow that this structure is going to be just intrinsically distilling out more and more coarse-grained information as it goes up, then maybe you want to query just stuff at that fine level. It doesn't quite work out if you think about what you're trying to do. Does everyone see that? Like, because in the UNet, you have this kind of reverse structure, and here the output is coming out here. So you could try something even more goofy. You could say, okay, maybe up here, this thing will have something that's going to look at what's the key value pairs generated by the lowest layer here. You could have them flipped in order. Lots of choices. I'm not going to dwell on these in the old style approaches, because I want to get to the transformer approaches later. But to answer your question, it's kind of a design choice of what do you want to have depend. For the most natural thing, if you just want to throw everything in there, is say this should be the input on the encoder side should be the concatenation of all the states, right, for the key value generation. Now, notice you have a choice, right? So you want to do this again, right? There's like layers here. So let's go to here to the next RNN layer. So this also should be attention here. Now you have a question, whether the attention here should have the same key value pairs as the one that you're doing here, or different key value pairs. Right? You could have different key value pairs that have their own MLPs associated with them, but depend on the same states. Because different ones might be wanting to bring different information into focus, more and more into focus for the purposes of the query. Okay? So all of this will allow information from the encoder side to be routed over to the decoder to aid in the generation of the next outputs, instead of having to have everything be captured by the states that cross over. So now you have lots of paths that are going to cross over. So in particular for training, right, each of these things has some output, is generating a Y1 pat. When you put the losses on top of here, the gradients will pass through not just down this way and through the state, but they'll also pass through attention over onto this side. Same way as in UNets, right? In UNets, the gradients flow all the way through, not just through the bottleneck, but through everything. So what it's telling the encoder is, hey, you don't just have to decide what you're going to distill out to go across the hidden state. You also have to give me good keys and values to use. But then again, if you do that, you don't have to have all the information inside of the hidden state if it's already captured and is appropriately queryable in the key value pairs. Okay, so it allows for training to happen potentially in a nicer way. Yeah, question?
So we can solve the problem of time gradients, the encoder like that, right? I mean, we are passing more to the encoder, but like, what about time gradients on the decoder that flows the
Okay, excellent question, right? So a way of looking at this, so we motivated it by UNet architecture, right? We said, hey, we want to make sure that we have access to the information. But there's a comment, because we've created these paths through attention, we also have gradients flowing through those paths. And when attention goes back to these key value pairs, it can reach back to right here, right? Directly through attention. It doesn't have to go through all of these things to get back here. And so the comment was, by doing this, we have added a way for gradients to not die when they're going backwards. Right? That information from here can flow all the way back in one hop through attention. So make sure everyone understands that part first, right? Any questions on that? The question is compound, so I'm going to answer it in pieces, but I want to make sure everyone follows. Everyone got that? So then the question is, hey, we've managed to give some kind of boost to the trainability of the encoder. But we haven't done that for the decoder. Because in the decoder, from here, when the gradient goes back, yes, the attention mechanism will send gradients back to the encoder, but we still have to propagate through the RNNs to get information into the decoder itself. Right? Excellent question. So actually, people thought about this, and they said, hey, wait, this is interesting, right? Now that I have this mechanism of accessing memory, why am I only accessing memory about the encoder? Right? Maybe I want to use this memory mechanism, this attention mechanism, to also look at local context at the decoder. Okay, does everyone see the motivation here? You can also be motivated by the gradients. I had this big problem of dying gradients. I have these LSTMs that are trying to like delicately balance how to get the gradients to not die without having too much of a lack of without having too much information from earlier flowing. So indeed, you can think about a second attention mechanism you can add in here. Right? So can add a second attention mechanism where the key value pairs come from the decoder. So instead of querying one memory, we can query two memories. Is that clear to everybody? How it's a natural design choice you might want to do? Okay. So here, you have an issue that's not that complicated, but we have to acknowledge it, which is that when you're looking at the memory, the key value pairs for Y2, right? For when you're doing the decoder this side. The only key value pairs you can have access to are the ones that come from the decoder before. Is that clear? Like you can't remember something in the future. Okay? Like this is not that complicated a thing, conceptually. So for this attention mechanism, note, it's almost like it's a note, right? Must be causal. You can't depend on the future. Again, this is not a conceptually challenging thing, but I want to make sure everyone gets it and doesn't get particularly confused about it, because it's not conceptually challenging, but it has some issues when it comes to implementing. Okay? Everyone see this? Has to be causal. Not a big deal. So there's a couple of design decisions you can have. One is that, so when something is causal, the question is, do you allow yourself to depend, like for example, let's look at this one here, Y2, okay? So let's think about over here. I'm gonna do a query on the second, so I have two queries, right? So one is looking back at the encoder, and one is looking at the decoder. So how many key value pairs should this have? Okay, it clearly should have a key value pair associated with the start, whatever was here, and the previous thing. So 2 for sure. But to be causal, it could have one more, right? It could also have one that comes from this particular step. Okay? So there's a couple of things here that you can think. In principle, you could have something which depends on this thing itself in your table. Kind of a weird thing. Like, why would you put something in that depends on, why are you querying something that you already have access to the input to the query? The input, why are you querying to pull something where you already have the thing there? Right? But you could do it for completeness, for example. Just like throw it in. So that's like one thing. One subtle point. Must be causal. So it has to be causal in two ways. Okay? So causal can only depend on previous and current time steps for decoding. But it also, once you've decided that you're going to potentially include current time steps, you can't depend on layers that are above you. Do you see that? Once you've decided that you also want to include the current time step, then you have to only depend on layers that are at your level or below. Okay? If include current time can only depend on layers below. So it says that for over here, for this attention mechanism, you can populate the keys and values based on the thing that's going to be input to the RNN, but not the output of the RNN, if you're going to follow this approach. Okay, so already in classical pictures of looking at the encoder-decoder architecture where you have everything running with an RNN, you already see that there are two kinds of ways that attention can be used. One in which, the first one we introduced, in which the key value pairs are coming from something different, like the encoder, and one in which the key value pairs are coming from the same structure that you're using. So these are distinguished with two names. The second attention mechanism is called self-attention. And because it's from the same thing. Okay, so this is the attention in which the key value pairs are populated in the decoder by the decoder itself. And then for the other one, for the other attention, the one we introduced first, is called cross-attention. As distinct from cross-attention. Where in cross-attention, the key value pairs are populated by something else. Okay? So that's an excellent question. Led me directly to the next thing I want to talk about, right? So if you do this, if you add the second attention, the self-attention mechanism at the decoder, then you have gradients, sort of coming inside here as well. So that might be nice. It's having the same effect. It's not forcing the state of the RNN to carry as much information. The state of the RNN at this point only has to carry, only in this picture has to carry like maybe some overall flow dynamics of the translated sentence. But once you think about this question, okay, once you've added this self-attention in the decoder, it is natural to wonder what information is actually needed in the RNN. I have memory that lets me look back at the previous things that my decoder was doing, which is the self-attention. I have cross memory that lets me look at what the encoder did. So what do I need my state for? Well, as of now, you need the state for one thing, right? Which is we've talked about these key value pairs as being something we throw into this pooling operation, like a hash table. They're like an unordered set, right? These are key value pairs. This is unordered. Unordered across I. Right? There's a key value. There's a key and value are distinct, but there's no ordering to this entire collection. It's just a set. Right? Look at the mechanism, right? We just look at it one at a time. It isn't like we look at the third and the first and the second. There's no list. Is that clear to everybody? Okay. So in that case, you could say, well, there's something minimal, at least, that the decoder's RNNs have to do. And they have to keep track of time. They have to count. Do you see that? Because then if they counted, then if these counted, then the state could then depend on time. Right? And time might be important because order might matter of what's going on. Like you might want to know, for example, in the decoder, what was the last thing I said? Right? Like what was the immediately previous thing? And so you want to have a query that would let you get the immediately previous thing. But that means that we have to know what time it is now and what time it was then, right? Does everyone see that? So this brings up one topic more that is useful in the context of attention, which is maybe, given that we know that time might be important, maybe we can add time directly into things. So rather than trying to, so there's a couple of approaches. One is we could say, and both approaches are actually done, by the way. One is to say, hey, this thing is set, takes a set as input. Maybe we can make this into a list and come up with a way of computing these these scores that took order into account. Choice one. Choice two, keep this as a set and somehow make sure that the keys and potentially the values include time. Does everyone see? That's like two choices of what you can do. So there's a trick that we use. So I'll describe this trick. It's called positional encoding. Which is how to add time to vectors. Now, there is the obvious way of adding time, okay? The obvious way of adding time is to have a counter and have it tick up by 1. Does everyone see how that's the choice? So I could add time with a one-dimensional thing. So idea 0. Just increment a counter. So start at 1, start at 0, 0 to 1 to 2 to 3, and so on. That would have time. Now, given what you know about neural nets and the way that we use them, can anyone tell me something that might be wrong with idea 0 of just having a counter? Counting up. Yeah. So you could have a question about parallelizing it. So positional encoding is something that we want to add kind of potentially just as input to the encoder and the decoder. Just give it access to what time it is as something that it knows, and then it can choose to embed that into the representations. So there really isn't a question of parallelizing this because, you know, how long will the input sequence be? You know, it'll be, you know, hundreds, thousands, tens, you know, 10,000, right? Some length long. There really isn't a question of parallelizing counting at that level. That's an issue. So we're not worried about that. Just think about it. Don't worry about the computation here, right? Computational issues. Think about what you know about how these things are built, what kind of values they like, things like that. Yeah.
Yeah, the values should be normalized like somewhere around 0. But at least what the layer prefers, which would probably be 0. And if the timer just timer values would overpower every other value, because they're not normalized runs.
Yeah, that's a great point, right? Points we've talked about when we talked about like HUD initialization, Xavier initialization, and so on. We said, look, we want values to be kind of hanging around 0, you know, in the near neighborhood of 0. And so if you do this, this will like have a value that goes up to like, you know, 999, you know, and 1,000, some numbers like this, which are huge compared to everything else. And we know, you know, from the perspective of gradient descent, you know, it's like a shiny object, right? Anything that's big is shiny, and they'll chase it. Right? And do you really want position to be the loudest thing in your system? Probably not. So you can't have these things getting up. So then you could say, okay, here's idea, let me call this -1, okay? Here's idea 0. Normalize idea 1. Idea -1, sorry. To make all the values small. But then you have another problem, which is that the distinction between 2 times, which might be very important, You know, for example, you might want to say, look at the last thing. It's like 1 in 1,000. It's like a tiny increment of difference, right? So that's also problematic. Yeah, question.
Is it also problematic that the later you get in the sequence, the more important the time is? Like the louder it becomes.
Yeah, similarly, this so there's two problems. One is that it asks you to make a fine distinction based on a tiny difference for nearby values, where you might think nearby times are actually very important if things are local. Second, even if you normalize, it still says that later in the sequence is louder. And why should later in the sequence louder matter? So it's like many problems here. So then you say, okay, do I have any other way to think about time? And the answer is yes, we do. That. Okay? So when you think about time there, in analog clocks, time is done with an hour hand, a minute hand, and a second hand. So time is in circles. Circular time. Does everyone see that? Like that way of time? So that way of time is circular time. So idea one is use circular time. So what's circular time? It just says, let me just, instead of having the time, I'll do e to the j omega t, complex number time. So I'll take my time, t, and I'll translate it into cosine and sine. By doing this, I will get a circle that moves at a certain rate for a particular omega. I can choose to move times fast or slow. And so we have vectors. I can choose many such vectors, right, with different omegas. So I can choose an hour hand that moves slowly. I can choose a minute hand that moves faster, and I can choose a second hand that moves very fast. And between all of these, I've embedded the time I want. So use circular time and have many, quote, hands. So vector time. So if you do this strategy, where you create a vector, which consists of cosines and sines at different frequencies, then you have something which will track time and will never have values that are getting too big or too small. It'll all be hanging around length 1, which is great in terms of what kind of functions, what kind of things you know that your neural net's like, in terms of where they can discriminate things. Okay? Any questions on the basic idea? Yeah.
This is you can also think of it as you also think of it as a modular operator. And if that's the case, is there going to be any repetition that you have to take note of running by test?
Yeah, great question. So the question was, if you look at this as an operation, it moves in a circle. And like the clock, the second hand will hit the same place repeatedly, like periodically. And so if you look at the second hand alone, you can't tell what time it is. Now, the hour hand will also repeat. So you do have an issue, which is that however big, whatever your smallest frequency omega is, you are caught between two things. On the one hand, if you make your smallest omega too small, what will happen is that you will never see certain qualitative values. So imagine if you had a century hand on the clock, okay? And so it moves, across, and in 12 centuries, it'll come back to 12, okay? In your lifetime, you would not really see that hand moving very much, okay? And so if you try to learn a pattern that depends on where that hand is, you might not actually learn to generalize, what happens later. You only have ever seen values that are in one place. Okay? Everyone see that? That's a real problem. Okay? And that's a problem with any embedding of time, actually. That's a standard problem of if you don't see something during training at all, you can't properly learn to extrapolate and generalize that at test time if you ever find something different. So if everything you've trained is on time periods that are very short, and now you want to generate out for something that's much longer, you're going to see what happens as you extrapolate. Right? You'll do something. And you can't necessarily know your dependence on time is what you want. So that is a problem. Okay? So the answer to that is you hope that you have the slowest thing of time be such that it wraps around a bit during the thing, so you don't learn to depend on it too much. And you hope that for generation, you don't have to depend on time that finely. Okay? So that's a great question. Similarly, if you make things too fast, but if you make it too fast, if you have a clock that only has a second hand, a millisecond hand, and a microsecond hand, it's not a very useful clock for taking track of how much time has passed in the class or what happened. It's like just spinning around too fast. So you do need to have like a mixture of different scales. Yeah.
Is it reasonable to scale the largest, smallest omega such that basically slowest clock makes one circle for the entire duration of the sequence, such that it varies between sequences?
Great question. The question was, is there a good rule of thumb to make the slowest clock be such that it makes one cycle through in the sort of length of the sequence? Right? The answer is a good rule of thumb. The challenge is you're going to have different length sequences in, for example, translation that you're going to be translating. So which sequence? You can go for the longest sequence, for example. Say whatever your longest sequence is that you're going to hold. Make it do one cycle in that time. That's a reasonable length. Yeah.
Can you make it vary per sequence so that each sequence has a different set of omega?
That's an excellent question, right? So I'll let you guys think about this, right? The question was, what if you made it vary with the length of the sequence? Different ones have different ones. Different sequences have different omegas. Is that a good idea or a bad idea? So to answer that question, let's think about things that you expect to want to be able to do easily, right? One thing you'd want to be able to do easily is to say, given my time index, right, that I have access to, what was the previous time? You want that calculation to be easy, right? Because you could argue that in many contexts, linguistics and so on, the immediately past time might be quite important. Like what was just happened. Do you see that? Does everyone see that? Or you might want to be able to add or subtract a particular number of time units. This is something you might want to be able to do easily. If the omegas are changing across sequences, that's going to be a hard operation to do. Because you don't have access to the omega. You just have access to the clock position. So for this reason, in positional encoding, when it's done this way using the circular time, one uses a single set of omegas for training. So final comment here that I want to make is when you're using circular time, because of this representation, actually a simple matrix multiply will actually can increment and decrement time because of rotation. So you can easily learn matrix. Since everything you're learning is matrix multiplies, it means that these kind of operations are really easy to learn. Like go back 3 time steps, go forward 1 time step. All that kind of stuff is very easy. So this is positional encoding. Now, there is another way of doing positional encoding that's also present in attention mechanisms, which would be to turn this unordered thing into a list and then have the scores actually have another term in them. And the other term should depend on the relative position difference between I, the thing that's coming in, and whatever position represents this query. So you have to have some position representing the query, and you have a difference between those two. and you add some term into the score. That's sometimes called relative position embedding, where what you do is you say, I'm going to use a relative position embedding, and you have a learnable weight that you add to how much to weight or put your finger on the scale in favor of or against a particular time, relative time. Neither of these is particularly very satisfying, but you need something. And so this is kind of your menu of choices. Yeah?
I was wondering, would you hold the positional embedding constant as you get it?
Great question is, how do you deal with the positional encoding and when does it enter? So one thing is that you can, natural thing is you give every single layer in access to its own vector, kind of extrinsically as another input. That's the positional embedding. That's one thing you could do. So you could have one of them that you use ever. You'd probably want to use the same one because you might want to be able to look down at the times that have been processed earlier. So you want to have everyone have the common sense of time. That's one approach. The other approach is to say, no, I'll just give a positional embedding at the beginning, and it's up to the system to propagate it up. Like it's a vector input. It can just propagate it up if it wants. Okay, and we'll talk more, when we talk about transformer architectures, we'll talk more about the details of it. But I just want you to be aware of this in the context of attention. There is this issue of position. And actually, just to lead to the key idea behind transformers, once people had the idea of positional encoding in their minds, then it was like, wait, if I have position and I have self-attention and cross-attention, how small can I make these RNNs? And the answer is, well, let's try the simplest approach, which would be, let's make the RNNs of size 0. Okay? I'll make the state have size 0. So if I make the state have size 0, then I've basically removed an RNN with state size 0, just an MLP. Right? There's like no more state. And so they said, let's try that. And amazingly, it worked. And that's why the paper that introduced the idea of transformers was entitled, Attention is All You Need. Because it was like, well, we have appropriate attention, balancing with the RNN states, but like what happens if we look at the extreme of just killing the RNNs to nothing? Does this still work? And the answer is it still does work. In fact, it works great. So that we'll talk about more when I talk about transformers. But before that, I wanted to get into this issue of self-supervision, which is really important. So maybe I'll tell you, why are we talking about self-supervision at this point? We could have talked about it earlier. The reason we're talking about it at this point is the attention mechanism, it's like a giant pool, giant pooling operation. And because it's like a giant pooling operation, it really doesn't have intrinsically very strong of an inductive bias. This is basically, another way to think about it is like a graph, right? This attention mechanism says that my input is like a fully connected graph. So if you think about when you learn functions and you say that, well, my function could depend on anything in my graph, let me just assume my structure is fully connected. Yes, you could have anything be a subset of a fully connected graph. But at the same time, you aren't really biasing towards any particular dependence. Do you see that? So when you have a strong inductive bias, you're biasing yourself towards certain kinds of patterns you want to learn. When you have a weak inductive bias, you're not. But in the presence of a weak inductive bias, you still have to learn something somehow. And one of the ways that you can learn, generically speaking, if you have a strong inductive bias, you can get away with less data. When you have a very weak inductive bias, the only thing you have to learn from is data. So you have to learn from more data. Okay? That sort of general story kind of clear? So because these attention type systems that we have don't really have that strong of an inductive bias, unlike a unit really does route you to a particular place, right? There's no problem in a unit. You have information that's local, that's the relevant information already being brought to you. Here, you have to learn what that routing is, right? Through getting appropriate key value pairs and appropriate queries. So these kind of things tend to want a lot of data to learn from. And in those situations, you, practically speaking, have a problem. And that problem is that you run out of data. So you have a task that you want to solve. And the task that you want to solve only has some amount of data. You might have a lot, it might be like 1,000 samples from your perspective. It's very hard for you to collect 1,000 samples, but you got 1,000 samples. But 1,000 might not be nearly enough if your system doesn't have a strong enough inductive bias. So what do you do? And in those settings, the key idea that people have, again, remember, deep learning is about looking where the light is. It's basically saying, well, I don't have labeled data. Okay, I don't have labeled data. Does that mean I don't work on the problem? Originally, yes. It meant you didn't work on the problem. But now you're like, well, can I get, what do I have? And the answer in many cases is I have a bunch of unlabeled data. Okay? So the question becomes, how can I train a network with unlabeled data? So from the perspective of everything we've talked about with backprop, what is the role of the labels? The role of the labels is critical because the labels show up in the loss, right? And the loss is the original source of where the gradients come from that backprop then distributes out to everything. So if you don't have labels in a traditional perspective on this, you're kind of dead, right? You don't have any loss. Because you don't have any loss, you don't have any gradients. Because you don't have any gradients, you can't do any updates. So how do you get yourself out of this mess, right, of not being able to do anything? That's where the idea of self-supervision comes from. This is why it's called self-supervision in the deep learning community. Because it says, maybe I can make up my own labels from my data. And I'll generate my own supervision. I'm still going to do supervised learning style, in which I'm going to have losses, I'm going to compute gradients, I'm going to do backprop, right? But I just won't have any labels given to me from the outside. I'll make my own. Okay? So self-supervision, one of the key ways of doing it is something called autoencoding, which we'll talk about. But for those of you who have taken a machine learning class, you might say, wait, isn't this just a fancy name for something else? And the answer is yes. This is unsupervised learning. So now let's talk about this. That's what we call unsupervised learning. So in traditional machine learning courses and historically for machine learning, unsupervised learning was considered its own different category of learning problems. And unsupervised learning was if you want to look back at the literature for unsupervised learning in older papers, one of the keywords you should look for is actually called data mining. I don't know if any of you heard this term, data mining? It might be out of memory for many of you, but it's there as a historical term. There's still communities that still use it, but I mean it's an older term for us now. But the idea of data mining was that in many contexts you have a bunch of data, and you don't know what patterns are in there, and so you want to go mining in the data to see, are there any useful, interesting patterns in this data? It's not that you have a particular target in mind. It's just like what's going on in this data. So unsupervised learning, you've learned about it in your classes, and you've probably learned two algorithms or two approaches for unsupervised learning. have learned, I'm assuming. One approach you've learned is basically PCA. PCA and friends. Okay? And PCA and friends are kind of dimensionality reduction. And the other thing you have learned is k-means and friends, which is clustering. Right? Am I right? So first, how many of you have seen PCA and friends dimensionality reduction somewhere? Probably everyone. How many of you have seen k-means and its friends? Some of you might not have seen any friends, or you probably not have seen no friends of PCA either. But as long as you know their like main version, you're good for what we need in this class. And so, what's interesting about it, historically a little bit, is when you learned these things, you had specialized algorithms for each of them. Okay, so it turns out for us, the one that's the most important for us to understand is actually PCA. That's the one that is kind of, you can root your intuition into what we do with self-supervision very strongly in PCA. I mean, k-means is not useless to think about, but it's not as important for us. So we're going to start with this one. So remember how you did PCA. So there's some business about demeaning your data. Okay, so you probably learned this. That you did first, look for a center. We're less interested in that. Then what you did was you take your data in a big matrix and you computed the SVD. So what you did was you said, here's my data matrix X, U, sigma V transpose. Suppose your data matrix was arranged so that you had samples this way and features this way. Okay, so like the way you set up for regression problems, right? You usually have your features on columns, and each row is a different data point. If you did this, then you said, look at largest singular values. Sigma 1 out to sigma k, the k biggest singular values. And you said, let's just keep those. So then you said that V1 through Vk, right? These are all, I don't know, D features and samples. These are all vectors in RD, right? And so what did they do? They project from feature space, d-dimensional feature space, to 1, each of them. Right? They're all orthogonal to each other. They're orthogonal. And we can use the I transpose X to get ith principal feature. of a new point x, potentially. So this is how you think about using PCA for dimensionality reduction, right? Everyone familiar with this? Right, you want to say that, look, what is it? What are you saying, though, when you do this? What you're saying is that you have this data, and it seems to live in a large d-dimensional space. But actually, by looking at it this way, you say that most of the variation is actually coming in these k dimensions. And so if you think that the things that are making your data points vary are actually also interesting, if you make that assumption, then you say that the interesting stuff is happening in only these k dimensions. So when we have a new point, this is how I use it for dimensionality reduction. When we have a new point, I can just look at what's happening in those k directions. Okay? Any questions on this? Like, I was recalling this from before. So this, when you use PCA for dimensionality reduction, this then lets you attack the problem that we started off motivated by. If you have a situation where you have not enough data that's labeled, but you might have access to lots more unlabeled data, it says that maybe now, instead of having to learn a regression function on these very, very large data points that you have, you can learn them on a much smaller data point that comes from after doing this dimensionality reduction. So again, think about your data points are actually like audio signals or something. They're audio signals that are like thousands of things long, and you're trying to do classification into like 3 or 4 things. You're like, okay, I don't want to do a classification, build a classifier on a 1,000 long thing. I'll dimensionality reduce to like 4 or 5 or 3 things, and we'll build a classifier there. And I hope that this will get me what I want. Okay, so this dimensionality reduction perspective is what we would like to get in deep learning. Because we want to be able to use a lot of data, hopefully, to have a system learn something sufficiently so that when we can then use it for a smaller amount of data to get the job done. Okay? Now, the problem we have is that nothing here looks like gradient descent. Okay? You look at this and you say, where's the loss? Where's the gradient? Where are the updates? And the answer is you don't see anything. Because all of the work is being done by this compute SVD, which is the black box to you, right? And it doesn't seem like it has any losses in it. So when we want to generalize what's going on here to something that we can then use for something nonlinear, like a neural net, we need to understand, like, why is this working? And once we understand why this is working, we can try to interpret it using a loss. Again, why do we want the loss? Because, again, deep learning is looking where the light is. We have PyTorch. If you give it a loss, you can compute gradients, and then it can like optimize things for you. So we really would like to be able to use PyTorch. Okay, like very simple. And if you look at this and you say, this was justified. By Eckert-Young. Mirsky theorem. Which said that the best rank K approximation to a matrix X is sum I equals 1 to K, sigma I, ui, vi transpose. Right? The Eckert-Young-Mirsky theorem that you might have seen, should have seen, says that this is justified because if I want to approximate a matrix X with a rank K matrix, I can just use this rank K matrix, and that's optimal. So what do you mean by best? Best approximation, you have to have a loss. This is why we care, right? Anytime you have a best, you have to have a way of ranking. And the easiest way of ranking is having a loss. Okay? So what does best mean? Best meant that this minimizes the matrix norm in X and X hat. Now, oftentimes in a class, when you learn Eckert-Young-Mirsky, you will learn this. So the problem with matrix norms is you have multiple matrix norms that are all interesting, right? And oftentimes, the first matrix norm you're taught as the interesting one is spectral norm, okay? And for spectral norm, you can write this 2 norm, you can see this, but spectral norm isn't as helpful for generalizing. But there's a more simpler norm, Frobenius norm. And this is also true for Frobenius norm. Frobenius norm is great. Because Frobenius norm is like a very dumb norm in terms of what it does. It just says, I'm going to treat the matrix as a big vector filled with numbers. And all I want to do is to make sure that these numbers are as close to those numbers as possible in squared error sense. That's great, right? Spectral norm is much more like, okay, like how much do you amplify different direction? Like, this is like, are these numbers close, right? And Eckert-Young-Mirsky holds for Frobenius norm, which means now you have a characterization of what this thing is doing in terms of a loss minimization. Okay? Because you can say that, hey, all I want to do is to have X itself encoded in some way that gives me X hat and make those two close to each other. This is the connection to autoencoders. Okay? So we can have a linear autoencoder. Imagine okay, so one more step we have to do, which is Eckert-Young-Mirsky tells us that the best rank K approximation is this. So we have to understand how can we represent a rank K approximation in PyTorch. Okay? Because what can you do? At the end of the day, all we can do in PyTorch is have a bunch of weights and tell gradient descent, like, go fix those weights to minimize my loss. That's it. That's all we can do. So we need a way of representing a rank K approximation using PyTorch. So the question becomes, if you have X in, what can I write here? So I want some function that has weights and X such that this thing is rank K. Best PyTorch will handle. In Frobenius norm, PyTorch will handle. But getting something being rank K, we have to do. Okay? In this way of thinking. So how can you get something that's guaranteed to be rank K if you do this? So here you think about rank for matrices as basically being the matrix viewed as a linear transformation. And what you want to do is to make sure that it has only K degrees of freedom that it can actually move in. So you can say, okay, I can do this. I can take X, a bunch of data. I can multiply it to get W1X, where this is small. I guess here I should match the notation that I have over there. So hold on. Let me tell you what x is. Okay? So most of us like, so this is the way we standardly think about it for regression. We put the samples as rows, and we put the features as columns. But because we like to think about data as being columns also, we have a problem with doing it this way. Okay? So what we're going to do is we're going to go to data as columns mode. So I'm going to think of x instead as these are features, and the different columns are n. So let's think of it this way. I'm changing now, so think of it this way. So if I do this, then I can think of x going to w1x, where w1 is a matrix, and I multiply x by the matrix, and I'm going to make it, so x originally has d columns that are d in size. Now I can make this thing be smaller in size. Okay? So I can make w1 have only k columns. Then I can take that and I can multiply it by w2. Where w2 has k rows, so I can get the, k columns, so I can get the matrix multiply to work. And I'll go back up to size d. Okay? So if you see this w1 has rank at most k. Is that clear to everybody? Because it only has k rows. Which means w2 times w1 also has rank at most k. Which means this whole thing has rank k. So now I have something which is PyTorch compatible. Two sets of weights, w2 and w1. And I can turn x into something which is rank k. And now I'm done, right? I'm off to the races. I can just tell PyTorch to minimize this. And I'm guaranteed to learn something that will be a way of taking data points and projecting them into k dimensions and then bringing them back out such that I get the best rank k approximation. And if PyTorch can solve this, it will give me this subspace that I need. Yeah.
You think eventually generally less computationally intensive as calculus?
Great question. The question is this less computationally intensive than computing the full SVD? That's actually a very good question, right? So if you think about this, this is a Frobenius norm, right? Because it's a Frobenius norm, it's just treating the entire matrix like a block of numbers, which means this thing itself is a sum over data points. The ith data point minus w2, w1, because the way that matrix multiplication works, xi squared. All right, so I'm answering your question about computation by saying, notice that this Frobenius norm is just a sum over data points. Good. Sum over data points. This is like a standard loss now. Which means not only can I do gradient descent, I can do SGD. So if I have a lot of data points, computing this SVD might be painful for me. But I can do SGD now. Look at a data point by data point. So I can get this thing to actually run. So it might be impossible for you to actually compute this SVD because it's too big. Your entire matrix might not fit in memory. Okay? But as long as each vector can fit in memory and you can encode W2 and W1 in memory, you can do SGD on this, which means you can definitely get this to run in many more settings than when you could run the SVD. Again, at least the straightforward ways of doing SVD. Okay, so with that, I will continue the discussion of autoencoding and things so in the homework, you see more variation. So this gives you the key idea. Once you understand that that by doing this, I can turn PCA-like things into encoding yourself, but forcing yourself to go through a bottleneck, then we're in really good shape. Because we can now generalize this to any deep network, as long as we basically have something we can come up with that's the counterpart of W2 and W1. We can do nonlinearities of any kind. So yeah, I'll talk more about this on Friday.